Welcome to lecture 20 of week 4. What we are going to do today is we will see another method for determination of deflection for statically determinate beam, and the method is moment area method. As you can see, this method was originally formulated by Otto Moore in 1868, which is almost 150 years ago. Now, we may ask a question that a method which was derived in 150 years ago and still we are using it in spite of having a lot of limitations. We will see those limitations anyway. Why still we are using this method or learning this method in this course, and similar many other methods in this course, which probably has many limitations as well. You leave the discussion for the last class of this entire course. We'll see what was the motivation of learning all these methods in spite of there are many limitations. Okay, so let us first understand the concept behind moment area method. But remember, as I said earlier, the premise of this method is the equation of elastic curve. Okay. Okay, if you have understood the equation of elastic curve and the bending moment shear force diagram, probably the understanding this concept will be very trivial. Now, you see, suppose again let us demonstrate this through simple supported beam, but that the similar concept can be extended to any other boundary conditions, any other loading conditions as well. Now, take a simply supported beam AB, and as per our sign convention, this is x positive, and we are, since assuming sagging is positive, so sagging means deflection is downward positive. So, this is our positive direction y downward, and suppose this is the deflected shape of the beam AB. Okay. Now, suppose take a point here, any point which is at a distance x from A, and suppose at that point deflection is y. So, we already discussed how this, what is the equation that represent these elastic the deflected shape of this beam, and that was the equation of elastic curve. Okay. Now, suppose draw a tangent at this point, okay, and then this angle will be theta, which is the slope at this point. Theta is equal to dy dx at this point. Now, please remember the sign convention. We are assuming theta, which is measured clockwise direction, as positive and anti-clockwise direction as negative. And if you see book, many books uses many other sign convention. Again, whatever sign convention you use, please be consistent with the sign convention. Now, so this is the angle, this is theta. Okay. Now, you take any point, if this point, any point you take, and at that point draw a slope, and this slope intersect at AB, and that angle made by the angle made by this slope and this line AB gives you the slope at that particular point. Well, now again this is theta. So, we know that theta is equal to dy dx, right, and remember the assumption theta is equal to dy dx was the deflection and slope are small. Therefore, curvature, the nonlinear term in the curvature can be neglected. Okay, and we also discussed the Euler-Bernoulli equation, which is the equation of elastic curve, as this. Okay. So, this is essentially the mathematical representation of this process, a beam which is deflected like this. Okay. Now, this equation now can also be written as like this, where d dx taken out and this is dy dx, and since dy dx is equal to theta, so we can say that d theta dx is equal to minus m by ei. Say this m by ei is phi x, because this is a function of x, that is why it is written as phi x. So, wherever we refer phi, it means m by ei. Okay. And now, m is anyway function of x, but ui this can also be function of x. So, together it is written as phi as a function of x. Okay. Now, phi x mx by I. Okay. Now, suppose this is the deflected shape of the beam, of any beam. Okay. Now, similarly, if you take 2 points at A and B and draw tangent at A and again draw tangent at B. Now, tangent at A makes an angle theta A with the initial profile or with the horizontal, and tangent at B makes an angle theta B. So, theta A is this direction, that is why it is positive, and this is written as minus theta B because it is measured anti-clockwise direction. Okay. So, theta A and theta B are essentially the slope at point A and at point B respectively, right. Now, suppose so this angle is theta AB. So, theta AB is the angle between the slope at A and at B. So, if you by just simple geometry we can say that theta B is essentially this angle plus this angle. So, theta A minus theta B. Okay. Now, suppose this is, which is say again, take projection of, this is the projection of A on slope at B, and this is the projection of B on slope drawn at A. Suppose they are A dash and B dash. So, A dash is essentially the it is also called that it is the deviation of A on slope drawn at B, and this is also of point B on slope drawn at A. Okay. Now, what is the physical significance of these 2 points it will be clear shortly. Suppose we have 2 points, such 2 points A dash and B dash, right. Now, this is this is denoted as delta BA, and similarly, so this is denoted as delta AB. So, this is essentially what? This is the distance between the point B and its projection on slope drawn at A, and this delta B is the distance between point A and its projection on slope drawn at B. Okay. Now, we know that d theta dx is equal to minus phi x. Just now we denoted this. Okay. Now, if we integrate it, the entire thing between point A and B, so what we get is integration of d theta between A and B is equal to minus integration of phi x between A to B, right. Now, what is this integration of d theta? Integration of d theta between point A to B is equal to theta B minus theta A, but since we have a minus sign here, so it can be written as theta A minus theta B, and the integration between A to B is phi x dx. So, what is theta A minus theta B? Theta A minus theta B essentially theta AB. So, this is theta AB is equal to integration of phi x between A and B, and theta. So, we can say that the angle between tangents drawn at A and B, which is theta B, is equal to this. So, what is the physical significance of this equation? Now, suppose this is the bending moment diagram, not the bending moment diagram, this is the bending moment diagram divided by EI. Okay. So, this is phi x. Okay. And now, then area of this curve is this between point A and B. So, integration of phi x dx between point A and B essentially this shaded area, right. So, what it says? It says that if we take 2 points A and B and draw tangent at those 2 points A and B, then the angle between those tangents will be the area between area of the M by EI diagram between these 2 points A and B, right. So, here we have the first theorem of moment area method. What it says, just now what I said, that the change in slope between the tangents drawn to the elastic curve at any 2 points A and B. So, any 2 points A and B, and the change in slope between these is theta AB, is equal to the area of bending moment diagram between A and B, area of bending moment diagram between A and B, and divided by EI. Okay. So, this is the first theorem of moment area method. When we see the application of this, probably it will be more clear. Okay, next let us see. So, the first theorem essentially gives you some information about the slope, right. Now, so theta AB. Let us see how to get some information about these two deflection. It is not in a deflection in true sense, but some measure of deflection, delta BA and delta AB. Okay. Now, this theorem says, right. Now, so take just first point, let us find out what is delta B, and the similar concept can be extended to delta AB as well. Now, so B dash, this point is essentially projection of B on slope drawn at A. So, we need to find out what will be the delta BA, right, and this is the bending moment diagram by bending moment diagram by EI, okay, and this is the area between two points A and B. So, yes, now take any arbitrary point between A and B, say that point is at a distance xb from B. Okay, so, it could be any point between A and B. Now, take a small segment which is of length delta x. So, this is delta s, and but as I said, deflection is small, delta s can be this curvilinear length, this arc length this length can be represented by delta x if your slope and deflection is small. So, suppose the small length of this small segment is delta x. Okay. So, and then the angle due to this length is d theta. Okay. So, if this is d theta, then let us draw, if we draw slopes at point this and at a distance delta x, then the angle between these slopes will also be d theta, that we have seen while deriving the equation of elastic curve, right. Now, so this angle is also d theta. If so, then what expression now, and suppose, and this distance is d of d delta BA. Now, if this point becomes A and this point becomes B, so naturally this point becomes delta BA, right. Now, essentially, so okay. Now, so we know that this length will be this xb into d theta, okay, and this is, we can write this if theta is very small, okay. So, this we can write. Now, so if this is, then if we integrate it between A to B, what we get is delta BA, and this integration will be xb d theta between B to A, okay, because xb is measured from B, okay. Now, so what this is exactly? Now, we know that d theta dx is equal to minus phi x. We have defined phi x like this. Let us substitute this in this expression. If we do that, then what we have is delta BA, which is the distance between point B and its projection B dash, which is drawn on slope at A. So, projection of B on slope at A, delta BA, that is equal to this. Now, what this expression is essentially the moment of this area about point A. If we do not have this, if we do not have xb, if had it been integration of A to B phi x dx, this was the area of this, the area between between A and B. But if we have xb into phi x dx, then this is essentially the moment of this area about, you see xb varies from A to B, Okay. Now, it was B to A initially, but it becomes A to B because of this minus sign. Now, if it is, then if this is the moment, if this is the moment of this area about B, then what we can write, delta BA is equal to that moment of this area from or about point B. Now, which is again can be written as xb bar cross area of this area into centroidal distance of this, the distance of centroid from B. So, that would be the moment of this area from B. Similarly, the moment of this area from A will be the area itself multiplied by the distance of centroid from A. So, delta BA will be x B bar, which is the distance of centroid from B, into area of this area between A and B. So, similarly, we can also determine delta AB is equal to x A bar, which is the centroidal distance from A, into area of this, and for different area I believe you know how to determine the centroidal distances. Okay. So, if it is, then what it says? It says that this distance, the projection of the distance between point B, or the deviation of point B on slope drawn at A, that is equal to the moment of M by EI diagram about point B. Okay. This gives you theorem 2. What it says that the deviation of any point B, relative to the tangent drawn to the elastic curve at any other point A. So, deviation of point B relative to the tangent drawn at A, and that deviation is delta BA here, in a direction perpendicular to the original position of the beam, which is anyway true because we are calculating direction in a perpendicular direction. Okay, is equal to the moment with respect to B, of the area of bending moment diagram divided by EI between A and B. So, this is the second theorem. So, moment area method is essentially, so these, if we look at this theorem, they do not say anything new about the behavior of the beam, because this behavior can be expressed through equation of elastic curve itself. It is some interpretation, a different interpretation of equation of elastic curve, and use that interpretation to determine slopes and deflection. Now, moment area method is essentially now is application of these two theorems just now we stated and proved. Okay, let us see one example, probably then it will be clear. Take a simply supported beam. We have already determined bending moment, slope and deflection of this beam using direct integration method. Right now, let us find out the slope and deflection using moment area method. So, expression of mx is this. Anyway, you have to determine any method you use. This is the how the bending moment varies. Now, suppose this is the deflection, this is the reflected shape of this beam, okay, and the reaction will be QL by 2, and QL by 2 it is symmetric, and suppose the midpoint C is the midpoint. If C is the midpoint, then we know due to symmetry the deflection will be maximum at the midpoint, and if we draw slope at point C, then this slope will be 0. Okay, because how do you calculate deflection? What is the position of maximum deflection? Where dy dx is equal to 0, means the dy dx is essentially the slope. So, slope is 0 at this point. Okay. So, let us draw one tangent at A and one tangent at C. So, this will be essentially the angle between tangent at A and C. So, it is essentially theta AC. Right, but since we know that theta AB was theta A minus theta B, but since in this case theta C is equal to 0, so this angle is essentially theta A. Okay. So, this angle is theta A. So, this angle is essentially slope at point A. Okay. Now, what the first theorem says? The first theorem says that if we draw tangent at 2 points, the angle between those two tangents will be the area of bending moment diagram, M by EI diagram between those 2 points. So, now between A and C, this is the bending moment diagram. We have also seen how to draw bending moment diagram for this case, and so this is the area of bending moment diagram between A and C, and the centroidal distance, centroid of this this parabolic curve is at a distance 5L by 16 from point A, because it is L by 2, this distance is L by 2. Okay. So, it is essentially the distance, if distance is L, then it is 5L by 8, but it is L by 2, so it is 5L by 16. Okay. So, the first is what will be theta AC, which is again in this case theta A, because theta C is equal to 0, will be the integration of XA, integration between A to C of bending moment, of area of bending moment diagram. And if we substitute bending moment diagram, just now we have we determined what is the bending moment diagram. So, if you substitute bending moment diagram, bending moment expression here and integrate between 0 to L by 2, we get expression of theta A is equal to this. And then what will be the delta? Again, you see in this case what that theorem says. The theorem says this deviation of any point with respect to the slope at any other point will be the moment of the bending moment M by EI diagram with respect to about that point. Now, so this is the slope at C, this is the slope at A. So, what would be the deviation of point C with respect to the slope at A? This deviation will be this distance, right. So, this, because this is the point, this is point C, the projection of point C on slope drawn at A. So, this will be this is the deviation, but in this case, in slope at C is equal to 0, this deviation itself is the deflection at C delta. So, delta will be the moment of this diagram, about point A. Please note that for calculating slope, it is very straightforward because it is the area, right. But when you calculate the deflection, since it is moment, about what point the moment is to be taken, that is very important, and that you need to decide based on what exactly you are calculating. In this case, you see, though it is deflection at point C, but we are looking this in a different way. How we are looking it? We are looking it as if it is the point, it is the projection of point A on the slope at C. So, this distance will be the moment of this about point A. So, if you multiply that, so this will be the delta for this. And if you remember, for simply supported beam, we determine using direct integration technique, the deflection at point B at the midpoint is 5L cube by 5QL cube by 384 EI. Okay. Now, what you need to determine, what is important here is, please there is a correction, this will be 5 QL to the power 4 by 380 EI, it won't be cube, it is 4. Okay. So, that this is moment area method. So, what exactly moment area method is? It is the same equation of elastic line, same differential equation, but it is interpreted in a different way. Instead of directly integrating the equation, the integration is still there, but that integration, since the interpretation is different, the step for integration is also different. But essentially, the premise of moment area method is the same as elastic equation of elastic curve. So, it was, so today what we have done is we have just introduced the moment area method and demonstrated it through one simple example, and the next class will probably give you few more examples, so that you can understand the moment area method in a better way. Okay, here we stop today. So, next class we will see some more example on moment area method. Okay, thank you.